Okay, this section, section 1.4, discusses the notion of continuity. And the types of things we're going to talk about are continuity or connectedness in an open interval in which the endpoints are not included, in a closed interval in which the endpoints are included, and we're also going to look at what are called one-sided limits. If you remember, when we looked for the solution for a limit, when we asked for that y value to which we were headed, we always asked to look from the left side and from the right side, and we wanted to be in agreement. That truly is the definition of a limit. Where were we headed when we came at x equals c from either side? A one-sided limit allows us to ask that question just from one side. So I could say, where was I headed when I came at it from the right side, and where was I when I came at it from the left side? What y value were we headed towards? And those don't necessarily have to be in agreement. So I want to begin by looking at this notion of continuity. And I think the best thing to do here is to define continuity and look at limits on an open interval. So looking at an open interval means that the endpoints are not necessarily included. So an open interval would look something like this, from A to B. And let's look at some of the scenarios here. Well, first of all, since the endpoint is not included on this curve, you can put an open circle here, and you put an open circle here, and maybe we have a nice continuous curve. And if you reach in here to x equals c, we could say a couple things about it. The first thing is that the f of c is very much computable. It's right here, that dot, it's L. I could also say that the limit as x approaches c on my function. Okay, let's do the approach. On the left side we approach, we are headed to y value L. On the right side we approach, we are headed to the y value L. And we got ourselves a match. So we could express continuity in this case at x equals c. So the continuity of my function f of x at x equals c, we have continuity when the limit as x approaches c of my function is equal to the actual function value itself. Now, there's more to that when we're talking about continuity. So f of c must be defined, the limit must exist, and the limit must match. So let's actually qualify that statement. So this must be defined, the limit must exist, and they must be equal to each other. We've just established continuity. Now, if you were an electrical engineer, you would say, or an electrician, continuity is the flow of electricity through a wire. And if you've broken continuity, if you have a discontinuity, you've got yourself a broken wire. The electricity is not going to flow, a light won't come on. But through this section of my wire at x equals c, we have perfect continuity. The electrons will flow and our light will light up. So mathematically, this is how we define continuity. F of c is defined as L. The limit exists and is also L. And you can see very clearly here that it is a complete circuit or a complete wire. Looking on our open interval some more, I do see other situations that might occur. Again, it's an open interval from A to B. So let's take a look here. Again, our endpoints are not included, but let's say that right here is another spot that's undefined. And the curve looks something like that. Well, if you come down here to x equals c, the first thing we can say about our function is that the f of c is undefined. And not because it's infinity. It's undefined because, well, there's nothing there. Normally, the reason it's undefined that causes a little open spot like that is that the indeterminate form is being calculated there. So this is usually the hallmark of an indeterminate form, like 0 over 0, infinity over infinity, even 1 to the infinity is the indeterminate form. So any of those indeterminate forms will get you a discontinuity or a little break along your function, along your wire. So let's answer a few questions about this. Now, first of all, because f of c is undefined, you already know that this curve has a discontinuity at x equals c. That part is immediately evident by evaluating the function. But let's evaluate the limit as x approaches c on my function. Even though the function blinks out of existence, I can answer this question. As I head from the left side, as I head from the right side, I think we're all in agreement that we are headed to some y value, which I'll call L. So the limit does exist. The limit exists, but the function does not. It's undefined. There are different kinds of discontinuities. We call them removable and non-removable. And that word is pretty powerful, those words, because it works both in the graphical presentation and it also works in the analytical or mathematical presentation. The same word has very good meaning with regards to this kind of discontinuity. So which kind of discontinuity is this one? Is it removable or non-removable? Now, to be a removable discontinuity, it means that you can remove it. By redefining the f of c to be some value, whatever value you like. Well, I think we would redefine the f of c to be L. So what happens is if you redefine f of c to be L, you have filled in the dot. And if you fill in the dot, you have removed the discontinuity and the electricity can flow again through that wire. What does that look like? So again, the endpoints are not included for now. This also is undefined for the moment. So here it is. Here's our curve flowing through here. And then it goes up here. And what happens is if you decide to redefine f of c to actually be L, this dot gets filled in. And in fact, it's continuous because the limit exists. Check. The limit is equal to the function value, in this case L. Check. And I probably should have stated this first. The function value is defined now. Check. So those are the hallmarks of a continuous curve. Function is defined at x equals c. The limit does exist because the roads are leading to the same location. In fact, the function value and the limit are the same. So that's a removable discontinuity. It means that with one dot, you can basically repair the discontinuity. Believe it or not, we're going to discuss how to do that mathematically. And it will work out pretty well. And in fact, the word removable will make even more sense when we do that. Now I want to discuss what is referred to as a non-removable discontinuity. This is what it looks like to be non-removable. If you're over here on an open interval a and b, if again, we're over here at x equals c, and that's where we want to evaluate our limit. What if the curve looks something like this? We had an asymptote there. And this curve shot right off the page like this. And then maybe it did the same thing here and shot off the page in that direction. Now, the first thing to note here is that the f of c is very much undefined, and that right away tells you discontinuity. There's a break. But is it a repairable break? Now, repairable means that you can redefine the f of c to connect these two wires. Before we get there, let's do our limit. The limit as x approaches c on our function equals, all right, let's get on our roads. This road points to positive infinity. This road points to negative infinity. We couldn't be in further disagreement here. They don't agree. So therefore, the limit does not exist. The limit does not exist. Now the question becomes, with one simple redefinition of f of c, one dot along this line, can I bridge the gap between these two? And the answer is no, I can't. I could put the dot here. That won't connect these two wires. I could put the dot here. There's no way, really, with one simple function definition to reestablish continuity. So we call this non-removable. Because I can't remove it. I can't fix it. I can't patch it. Okay, so you've seen examples of removable discontinuities, of non-removable discontinuities. I think I want to do maybe one more quick example on an open interval, and I want to see if you can figure out what kind of discontinuity we have. Let's take a look at this one right here. And then we'll look at some other maybe closed intervals or one-sided limits. Here's one more, guys. Let's do this one quickly. Here's a nice open interval. We don't really care or look at the endpoints. We just sort of hang our wires here, our function. And again, there's a nice little break somewhere in there at x equals c. And then actually, this function just happens to be defined right there. So it's k, and this is L. So let's go through the list of checks for continuity. First check is the function defined at x equals c? The answer is, why, yes, it is. It's way up there at k. The second, so that's a check. Does the limit exist at x equals c? We approach, x approaches c. We come at the road from the left side. We come at it from the road from the right side. We're all in agreement. We were headed to L when it jumped up to k. We don't care where it is up there. We just care where we were headed. So yes, the limit exists. And then the third requirement, does the function value equal the answer for the limit? And the answer is no. So we couldn't pass all three checks. This is definitely a discontinuity, guys. Definitely a discontinuity. So here's my question for you. Is that a removable or non-removable? Can you redefine f of c to bridge the gap? And the answer is yes, you can. We can take this dot and redefine its y value as that y value. Now, we'll talk about how to do that mathematically, but at least graphically, you pick this dot up and drop it right in the hole, and you have reestablished continuity. So therefore, this is a removable discontinuity. So I need you to remember something. Removable means that you are capable of removing the discontinuity. Whether it's graphically or mathematically, we redefine the f of c. Okay. So I'd like to take a look at a couple of functions here, and I want to see if you can decide whether or not we have ourselves a removable or non-removable discontinuity at a particular x value. So let me give you an example here. f of x equals x squared minus 4 divided by x minus 2. Number one, where is the discontinuity? A quick way to know where discontinuity is to find the x values that cause you to divide by 0. That will always cause a discontinuity. Removable, non-removable, infinity, indeterminate form, all of the above are discontinuities. So we quickly go here and say, well, when is it true that we would divide by 0? Well, when x minus 2 is equal to 0. X equals 2 is definitely the site of a discontinuity. But what kind of discontinuity? That's the real question. So first of all, what is the f of 2? The f of 2 is 2 squared minus 4 over 2 minus 2, which is 4 minus 4 over 2 minus 2 is 0 over 0. So it's undefined. That immediately means it's a discontinuity. But more importantly, what's the limit? The limit as x approaches 2 on x squared minus 4 over x minus 2. So I always would like you to start limits using direct substitution. Let's do that. It's pretty much what we did just a moment ago. Now, what do you do when you encounter the indeterminate form on a limit? You cross it off. Do not say that the limit does not exist. The limit very much does exist. What does 0 over 0 look like on a graph again? That's what it looks like when we run into these indeterminate forms. And generally that screams out that there is an answer out there, we just don't know what it is. So always cross off the indeterminate form for a limit. Always dig deeper. Okay, don't write DNE for that. So how do we do this one? This one is the dividing out technique. So let's factor the top. Let's factor the bottom. We can't really factor the bottom. So what did you find in here? The offending factor. And I want to show you what I'm about to do with the offending factor. I'm going to remove it. So if you remove the offending factor, I can evaluate the limit now. Okay, so what kind of discontinuity do you think we have? I just removed the offending factor. And if you can remove the offending factor, you really have removed the discontinuity. It's a removable discontinuity. So analytically, that word remove works really, really well. This is removable. And what do removable discontinuities typically look like? Like this, a small break or gap that can be patched. Of course, because 0 over 0 looks like that as well. So if you can remove the offending factors, then you have removed the discontinuity. So what did we, in a sense, do there? Apparently, x squared minus 4 over x minus 2, you have to evaluate the function as it's written, and when I evaluate that function at x equals 2, it's undefined. So I already know there's a break at x equals 2. But when you divide these functions out and you remove the offending factor, you get a new function. Actually, let's call this one g. And g of x is just x plus 2, a nice, well-behaved function. What does it look like? Well, it's a line that has a y-intercept of 2 and a rise over run of 1. So let me graph that line in here. So what's the difference between g of x, where the g of 2 is just fine? The g of 2 is 4, and our original function f of x. Well, f of x is x squared minus 4 over x minus 2. which when you divide out those factors does give you x plus 2, but let's not forget the way this was originally written, x equals 2 is not in the domain. So here's what the original function looks like. It is a line with a y-intercept of 2, with a rise over run of 1. We'll put that point there at 3. Another rise over run, but there's an open circle right there. So if we connect the dots with a line, the line keeps going, but right here at x equals 2, you're supposed to have a discontinuity, and there it is. There is a break in the original curve. So here's the real crux of what I'm trying to get at, and that is that by removing the offending factor, you're actually filling in that little dot. You're removing the discontinuity. So the word remove works very well in that context. Here's the original function with the hole in place. Here it is filled in. We have removed the discontinuity, and we've gotten this version of the function here. So removing the offending factor literally removes the hole from your curve, actually takes it away. Therefore, it is definitely a removable discontinuity. Okay. So, proceeding forward here, I want to take a look now at one-sided limits. And a one-sided limit is where we get to approach a certain x value from one side or the other, and we don't have to be in agreement to have a one-sided limit. So let's take a look at what a one-sided limit perhaps looks like. Take a look at this curve. I'm going to make this y value k. I'll make this y value L. And of course, down here, this is x equals c. And let me ask you a few questions. First of all, the f of c happens to be defined. It's L. It's right here. Now, if I left that as an open circle, this would be undefined, but it is okay. The limit as x approaches c, it's a different matter. If I approach from the left side, I believe that I'm headed towards y value L. If I approach from the right side, I believe I'm headed to y value k. I'm not in agreement, therefore, this overall limit does not exist. Now, we have such a thing as a one-sided limit. And if you want to approach c from the left side, we put a little minus sign right there because, after all, you're kind of coming from negative territory and making your way from the left side. And you can say, just tell me from the left side, where was I headed? Well, if you only get on this left-sided road, you're headed to L. We can also do a one-sided limit as x approaches c from the right side. So we put a little plus there because we're heading from very positive x territory over here, and we're making our way to the left. Well, if you approach from the right side, it seems to me that the road leads to y value k. So this comes at it from the left. Here we're coming at it from the right. And now it's very clear that one-sided limits are not in agreement. So in order for this limit to exist, it would seem logical to imply that the limit as x approaches c from the left side must be equal to the limit as x approaches c from the right side. This is basically saying more formally what I've been saying all along, and that is if you want an overall limit, then basically you need to have agreement from both the left and the right side. And we can now say that mathematically. Okay. Now, I want to take a look at a few functions and their one-sided limits. Let's take a look at the function that defines the top half of a circle. So the top half of a circle can be defined as this. And what you're going to get in that scenario is just the top part of the circle. It's a function. It's a radius 2. This is defined here, this is defined here, this is defined here, but it is a function, so you will only get the top half, you won't get the bottom half, otherwise it's not considered to be a function. A couple questions for you about limits. Let's take a look at the limit as x approaches -2 from the right side. That means get on the road from the right and discuss where you think you're headed. Whether you get there or not doesn't really matter. It looks to me like we were headed to 0. Let's do the same thing and approach -2 from the left side. That's over here somewhere. Guys, where's the road to get on to approach from the left side? There is no road. So I'm trying to get to it from the left, and I don't even know where the on-ramp is. I can't do it. So that limit does not exist because I can't even get started. So what do you think about this question here? Is the answer to this question 0 or does not exist? I very much see the point right there. Look at that. The function screaming out 0. I'm 0 right now, so wouldn't the limit be 0 also on a well-behaved curve like that? No. The answer does not exist. Think about why. In order for the overall limit to exist, the one-sided limits must match each other. And this is what I've been saying informally before. You know, when you come at it from the left and right, you have to point to the same y value. These one-sided limits, they're not really in agreement. So that's a good example of a one-sided limit and, in fact, a limit that you can't even really work on because you can't, there's no function over there. Okay. Now, the one last thing I'm going to leave you with in this video, I'm going to take a look at the intermediate value theorem. Now, the intermediate value theorem states the following. If a function is continuous on a closed interval, and you look at the endpoint x values and they compute to get your endpoint y values, and as long as your curve is continuous, then some intermediate x value better give me an intermediate or middle y value as well. So let's see if we can use this intermediate value theorem. First, let me write the definition down here. Or actually, I'll flash it up here for you. We can all take a look at it here. So the intermediate value theorem says if the function is continuous on a closed interval and the endpoint y values do not match, the endpoint y values do not match, f of a is not equal to f of b. So f of a and f of b are the endpoint y values. Let's make them not match. We want our function to be continuous. That means no breaks. Now, if k is a number, a y value, between these two beginning and ending y values, the intermediate value theorem says there must be an x value c on my interval that yields that particular y value. Now, it's a lot to say, but it's easier to see graphically. Let's take a look at a graphical representation of that. Okay, The intermediate value theorem says your function must be continuous. We're going to have a closed interval. We're going to include the a, include the b. F of a is not allowed to be equal to the f of b. So let's make them different. Okay, if you want, we can label them. That's k, let's say, and this is L. We're allowed to do that. Make this capital K. Now, this works only on continuous curves. So let's draw a continuous curve, connect the dots. You can't leave the pen from the paper, and let's make it a function. So it's got to pass the vertical line test as well. And there we go, nice continuous connection. What the intermediate value theorem says is that there's some value of y, lowercase k, that lives between the top and bottom values. Here it is. And it promises you that there's at least one x value that lives in between a and b. There's at least one x value that lives between a and b. That's the intermediate value theorem stated graphically. And I think you can see that that would work only if the curve were continuous. Let's try it again with a discontinuous curve and see that the intermediate value theorem will not work necessarily. So I'm going to put f of a here. I'll put f of b way up there. And this time let's make a break. Discontinuity. We'll make it non-removable. Okay, so that's a discontinuous curve, or there's a discontinuity or break in it. And what's happening is I now try the same thing. I go in the middle here, and I get a lowercase k that lives between capital K and lowercase l, and you'll notice there is no value of c or x where the f of c is equal to that lowercase k. So it has to be continuous in order for this to work. Now, where could we use the intermediate value theorem? Where's a good place to use it? Well, a good place to use it might be right here. Let me take a look here. We have an example. Hang on a second here. There we go. A good example is finding zeros of a polynomial. So I'm going to give you a polynomial function, and we're going to prove that there must be a zero somewhere between two x values. So f of x, x cubed plus 2x minus 1. Let's try that, and we'll finish with that. So here's a function, and this function might have some zeros. In other words, where the y value is 0. This function is continuous. It is a polynomial known to be continuous, so it's a continuous curve. If I were to look at the f of 0, what do we get? If I were to look at the f of 1, what do we get? So where's the implication here? The implication is at x equals 0, the y value is 1. Let's place that right here. At x equals 1, I'm sorry, the y value is negative 1. My apologies. It goes here. At x equals 1, the y value is up here at 2. So forget that point right there. So what's going on here is you've got a continuous curve that has to connect the dots between here and here. A negative y value, and up here a positive y value. Well, if it's a continuous curve, we know it's continuous because it's a polynomial. Somewhere it's got to pass through the x-axis. There must be a 0 here. There must be a 0. So the intermediate value theorem says that because it's a continuous curve, because the y value went from negative 1 all the way up to positive 2, it must pass continuously through y equals 0 somewhere, and therefore there must be a 0 that lives between 0 and 1. I'm not saying I know what that 0 is. The intermediate value theorem won't maybe provide the 0, but it promises there's at least one 0 in there. There actually could be more than one 0, but there's probably just one in this example. Take a look at this, for example. What if we had another curve that did the same thing? It had a negative 1 here at x equals 0. It had a positive 2 here at x equals 1. But what if it, even though it was continuous, it oscillated a little bit? I just picked up 1, 2, 3 zeros. So I think the promise here is I promise you here at least one 0. Maybe more. If it's a function that's continuous, it could actually be more. So I'm just going to finish with this one last attempt here to find those zeros and to see if indeed it does live between 0 and 1. So I'm going to show you how to do that with the calculator here. So my calculator is the TI-83 has a solver. So if I go to my solver, you'll notice that it says equals 0 up there. So let me clear out the function. Clear it out. So what I want equal to 0 is going to be x cubed plus 2x minus 1. And then I'm going to hit second function, actually alpha. I hit alpha, and down here hit solve. See, it says solve down there. So now it says, all right, well, give me a starting point, and I'll start it at 0, let's say. Actually, it's still stuck in alpha here, so let's start it at 1 or 0. It doesn't really matter. And now I'm going to say alpha solve. Oops. What happened there? There we go. So what we got was 0.2617. We found a 0. And it is between 0 and 1, as promised by the intermediate value theorem. I'm going to hit graph here quickly so you can see it. Let me get the window correct. We're going to go from x equals 0 to x equals 1. We're going to go from y equals negative 1 to y equals 2. So we should see that little window, and the curve should come up here. And we should see it. Oh, I don't have the right curve in there. Give me 1 second to punch that in. X cubed plus 2x minus 1. There we go. So there's the curve that we just drew. Here's the negative 1y value. Here's the positive 2y value. The promise from the mean value theorem is that or intermediate value theorem, that it has to go through there and has to pick up a 0, and it did. Okay, that's it for this video. Sorry it went on a little bit long here, a little bit lengthy. Please definitely read this chapter completely and look at the notes online. Work on the homework, and let me know if you have any questions. Thanks very much, everyone.